Oh, hi there. So today I want to look at a new topic, one we haven't quite covered, but you've seen coming for a couple days now. And that, of course, is specifically this: naming covalent compounds, which isn't actually that bad compared to what we've been doing. Compared to ionic nomenclature, or even worse, this bonding idea of what is covalence, what is diatomicity, what are these concepts we've been talking about for the last couple days. This is really a nice step backwards, and especially a few of you have done it. Now, your sub should have handed you a white sheet already labeled naming covalent compounds. These are your notes for today. They've got a little piece of the periodic table, a grid on the back. I highly encourage you to fill them out. They're yours, but they'll really help on the homework and the test, and if you don't do them, well, you're pretty much stuck in class looking at me on a screen talking anyway, so at least this is something to do. And really, this is a pretty straightforward topic compared to everything. Now, we need to understand what we're talking about before we do anything else, and that is, of course, what even is a covalent compound? So a reminder is that covalency is pretty straightforward. It's two nonmetals. Let me fix this for just a second. Much better. A covalent is two nonmetals that are willing to share valence electrons. And they have to be nonmetals. Metals don't do covalent bonding, at least in any form we're going to be concerned about. So we have two nonmetals bound together, and that makes it really easy to identify if something is covalent or not. Namely, does it have a metal in it? If you've got a metal, you're not covalent. And now you're used to looking at a periodic table, but you aren't generally going to actually be asked that. You're going to look at a compound and determine if it's a metal or a nonmetal. So on your sheet here, again, I've given you a little block here. And let's just check if these compounds are ionic or covalent. And to do that, again, we're going to need to change them. So here we go. I mean, this is just magic. Now, we have the first four compounds I've listed here. We've got sodium chloride, sulfur tetrafluoride, carbon dioxide, and potassium permanganate. And what we're going to do is determine if these happen to be ionic or covalent. And generally, when I'm doing this personally, I am looking at the beginning of my compound. That is my cation ion if it's an ionic compound, and we really don't have a name for that if it's covalent, but I'm looking for the kind of the first capital letter, the first element in the compound. So on this first one, I have NaCl, sodium chloride, and I'm going to say this is an ionic compound specifically because sodium is a metal. How do I know it's a metal? Well, on the periodic table, which I don't have around here for a second, so hey, will you look at that? Now, sodium is a metal because it's all the way over here, all the way away from the noble gases. And that's nice, because it's easy to memorize. But some of them I'm not so sure, and so one thing I could do is look at the ion sheet. Is Na in the cation, the positive sheet? Oh yeah, look at that, it's Na+. Okay, it's a metal. I can't even use it for anything besides ions. I know this cannot be covalent. So all I'm asking you to do in this top section is circle which thing it is, ionic or covalent. As a matter of fact, you're going to be asked to do that for every single compound on the test. It's a half a point here and a half a point there. It's just going to add up 3 points. Unless you don't know how to do it, in which case you're absolutely dead. Now, SF4, you might be thinking, Mr. Nendick, S is on the ion sheet, so is F. S makes a -2 charge, it's called sulfide, and F makes a -1, it's fluoride, so of course this has to be ionic. But I've circled covalent. And a good trick to think about here is by looking at the little sheet I've given you up top here, you'll see, of course, that sulfur and fluorine, I think I'm pointing more or less to the right spots there, that sulfur and fluorine are both nonmetals. Well, how do you know that? Because, well, they're listed on the thing labeled, I don't know, the nonmetals. Beyond that, though, they're on the noble gas side of the staircase on your periodic table. So they have to both be nonmetals, and because they're both nonmetals, I don't get a choice besides covalent. So I know this sulfur and this fluorine, instead of completely losing or gaining electrons, are sharing them somehow. I don't know exactly how. It doesn't really matter, because when I go to name it, I know I'm not going to call this something like sulfur fluoride or something like that. I'm going to call this sulfur tetrafluoride, and we'll get to how I know that in a moment. In the same way, you might be thinking, oh, look, carbon oxide or carbon peroxide or carbon dioxide. One of those sounds a little different. It doesn't really matter what you do. I know, again, by just looking at my sheet of what's metals and not, that carbon is a nonmetal and oxygen is a nonmetal. And because I've got two nonmetals, it has to be covalent. Which leaves me potassium permanganate down here, KMnO4. Well, potassium's a metal. It's on the ion sheet as a positive. I also know that because on my Periodic table, here's potassium, all the way on the far side, as far from the noble gases as possible. So it's got to be a metal. And because this is a metal, that instantly disqualifies it from being covalent, so I have to say it's ionic. Now, I've given you a few more here, 5 more. And I want you quickly, in the next like 2 or 3 minutes, I'll give you a little intermission here in the film to tell me if these are ionic or covalent, and then we'll check my answers against the board. By the way, the hole puncher and I are still fighting, so this last one here, you might want to fix it. It says SnS2. So that's tin 4 sulfide, SnS2. Otherwise, you're not going to be able to do it. So I'll give you, let's say, actually closer to like a minute. These don't take that long to figure out if these are ionic or covalent, and at the end of that time, it will reappear here. All right, so here you go. P4O10, non-metal, non-metal. That means this is covalent. PbNO32, lead is a metal. Because it's a metal, this has to be ionic. LiBr, lithium's a metal, this has to be ionic. XeF2, that's a weird one. Xe is a noble gas, it can't react with anything. Mr. Nendick, were you sure you meant to type? Yeah, actually, some noble gases react with fluorine. Fluorine really is attractive, and it just gets all the other chemicals. It's, well, fluorine. So here we are, fluorine, kind of the opposite of Mr. Nendick here. We have 2 chemicals that are both nonmetals. So they like each other, they're going to share their electrons, and because they're sharing electrons, it's of course covalent, which leaves us our business of SNS2. Hopefully you wrote that down, that's metal, because, well, tin's a metal. And so that's an ionic. So those should be the answers to those, and hopefully you feel pretty good about those. If you don't, the stuff I'm going to give you tomorrow and the quiz on Friday are going to actually be a bit difficult. So make sure you get some help from a partner or shoot me an email or something like that. But it should be as easy as looking at the beginning and saying, is my first chemical metal or non-metal? Wow, I just teleported there for a second. Give me a second. All right, that's better. So we need to move on. And honestly, this isn't so bad yet. Actually, it doesn't really get that bad at all today. We need to quickly get this block of text here so we can get on to naming things. That's really what we're after today. Now, you're going to notice that covalent compounds, when you're looking at that first letter, either a metal or a non-metal. But really it comes down to covalent compounds do not contain ions in any form. So if you have something that has an ion in it, especially in that first spot, you know it doesn't have covalency. Because ions and covalent are diametrically opposed. It's one or the other. So because of that, because we don't have ions, we can't use the ion sheet. Easy enough. But that begs the question. If you don't have the ion sheet, how do I name things? Because so far we've been naming things. The only thing we've used is the ion sheet, and it comes out that all you need is, well, this piece of paper here that I can't pick up, the periodic table. So instead of using the ion sheet, we're going to use the periodic table. That's so easy. Well, yeah, and the only little caveat is you also need to memorize this little table down here in addition to the periodic table. So think about it. I'm using the periodic table. I must also be using this table, which is a table of prefixes. Prefixes just go at the beginning of a word and modify them to make them a different word. And in chemistry, our prefixes are based on numbers. And you are going to need to memorize these. Actually, you're going to need to memorize these by Friday, which sounds unreasonable at first class to a high school sophomore until you remember you're using them all day today and all day tomorrow in a full work period. It's only 10 things to memorize. It's not too bad. Look, mono, di, tri, 1, 2, 3, easy. Tetra, 4, that's weird. Penta, hexa, hepta, octa, nona, deca. Mr. Knight, you just looked at the sheet. You expect us to memorize these? Well, I've also not looked at them for a year. But it's not bad. Because you know what? Instead of looking at a sheet, I was actually looking at what to do next too, which is talk about the fact that you know some of these things. You know a triangle has 3 sides, and a pentagon has 5 sides, and a hexagon has 6, and an octagon has 8. Well, look at that. Tri, penta, hexa, octa. I already know 4 of the 10 prefixes from geometry. I have to know a decade is 10 years, and the word deca is in there. I can't imagine why. Latin's weird or something. So 5 of them. Mono, 6. I think most of us know that. Di seems pretty common, 7. So we really have to memorize 3 things, right? We got tetra for 4, which maybe you know the word tetrahedron, which we're thinking is down 2. These are just hepta for 7. Hepta's weird. And nona for 9. Maybe you know that word not. But honestly, you probably know these already. But we're going to use these prefixes. Now, here's the problem. It's going to take a little warning. Your temptation is going to be to revert to these prefixes and use them in ionic compounds. Please don't. There's a million ways I can make your life miserable as a teacher who has access to chemicals. It's like 3 ways you can make my life miserable as a high school student. And saying something like, I don't know, diammonium nitrate doesn't exist would be awful, or worse, diammonium dichromate. Oh my heart. It's awful. Don't do it. Don't. Please, don't. You'll miss points, and I'll just sit here crying a little bit while I grade it, and both things are unfortunate. Be clear. If it's covalent, you're allowed to use prefixes. If it's ionic, don't use the prefixes, please. Okay. Let's take like a 15-second mental break, flip over the paper, and then we'll get started on the next part of this. All right, so I want to work on actually naming these. I've given you everything you need to name these on the top. It's going to be really helpful in your homework tonight, on the study guide tomorrow, but you won't actually have that on Friday. Now, I'll give you an ion sheet for ionics. I'm not expecting you to memorize it, but this stuff I kind of expect you to have committed to memory because it's more straightforward and ties into information you've already used. So at the top, you've got that table of the prefixes. And then you've got a rule. Prefix plus first element name, and then after that, use prefix root I to name them. And that's what's going to go on. I think it's easier to see that by doing it. This is up here just as a reminder for you. The other thing to notice is what I mean by root plus I. So let's take a look at an example over here. Bromine. Now, bromine's an element. And when I talk about the root, I mean actually the stem of the word, which of course is going to be the beginning. Now in bromine, it's brom, but whatever. Generally, in an element, if it's a normal element, you're just going to drop the "ine." You're going to turn it over. So I can turn my root of bromine into this, and then add "ide," something like this. So I get bromide. So bromine becomes bromide. Now I only do this to the second one. Do not do this to the beginning. This is only the ending part. The first part's just the element's name. Right? So only the second element in the compound. Most of them are pretty common. A couple of common mistakes would be someone to write like oxygen becomes oxygide, but that just sounds bad. So we don't do it, we call it oxide. Or phosphoride. It just doesn't roll off the tongue, we call it phosphide, which is easier. This isn't too bad, and the best way to get used to it is to just do it. So I think that's a good thing. And because of that, let's go ahead and take a look at our table again. And let's go ahead and use that with our formula, which looks something like this. And let's apply it. So I want to look at one of the easiest covalent compounds, which is CO2. So I see prefix plus element name. So if you want to think about it, this part here has to apply to the beginning. And this part here has to apply to the end. So if I have CO2, I'm not even looking at the O2 at all. I'm only looking at the C, and I'm going to take the prefix plus the element name. Well, C, I know, is carbon. And O is oxygen. So my name is going to be something like carbon oxygen. But I need a prefix here, and there's 2 of them. So I'm going to have carbon dioxygen. Wait, oxygen isn't right. I've got to make that oxide. All right, cool. I'm done. Carbon dioxide. Sounds familiar. Mr. Knight, you made a terrible mistake. You forgot the prefix. It should be monocarbon dioxide. No. That's an extra bit of work I'm not willing to do. See, if the prefix on the first one is just a 1, we don't write it there because we just assume the element doesn't have a prefix at that point. It also just doesn't sound good. Monocarbon dioxide versus carbon dioxide. It just makes more sense to call it carbon dioxide. Now, cool. I've got that. But does that work for everything? Is everything that easy? Let's look at another option. Let's take a look at this chemical right here, which is SeBr4. So I look at my periodic table because maybe I don't know what the element Sc is. It's a nonmetal, it's between arsenic and bromine, and it happens to be called selenium, which is kind of hard to spell, but it's Selenium. Selenium. Not an element we use very frequently, but whatever, we're learning how to name everything, not just the things we use all the time. And then Br is pretty clearly bromine, which we're not going to write bromine, we're going to use bromide because it's the second part. Why don't we call this selenide? Because it's the first part. Remember, the first one's just the name, followed by the root "ide." So, bromide. So I have some form of selenium bromide, and the question is what form I have. And of course, I've got 4 of these bromines, so I look up at my table at the top, and I see 4. Oh yeah, that's called tetra. So I'm going to have selenium tetrabromide. Fell off the screen there for a second, my apologies. All we're doing is reading across and translating into what we know. Now, notice it's not monoselenium bromide. Please don't put mono on the beginning. It's not selenide tetrabromide here. Don't use the prefix in the beginning. It's not selenium tetrabromine. Actually, it ends in "ide" at the end of the sentence. I feel like this is getting pretty easy, Mr. Nennick. That's great. Let's kick it up one level. That extra level is going to be this. Of P2O5. I know it's covalent, non-metal, and non-metal. I know that N there. I've got penta-oxygen, pentaoxide. So now my end is going to be penta for the 5 oxygens, oxy as my root, ending in "ide." Wait a minute, I don't put a Y in oxygen. Just call it "ide." So I've got pentaoxide. English does have some sonaresis in it, so if you want to call it pentoxide, P-N-T-O-X-I-D-E, that's fine too, although properly I'll accept pentaoxide. It doesn't really matter. And that leaves me behind this P2 business. P is phosphorus, I know that. But I can't just say phosphorus pentaoxide. I have this 2 here, and phosphorus pentaoxide, of course, would be, well, this. But that's not what I was given. I was given P2O5. So I've got to reflect that there's 2 phosphorus, and because I now have ambiguity in what my chemical is, I have to get rid of it. So I have to call this diphosphorus pentoxide. Now, that might seem a little weird to you. Like, why am I only including? Because now I have to include a prefix. Because if I didn't, I don't know how many phosphoruses I have. Every one of these just becomes the same problem again and again. And to prove that to you, we can take a look at this in AS4O10. So this isn't too bad a name. Let's just do it right across. AS4. I've got 4 of them, so I need the prefix tetra. And then I've got AS, so that's arsenic. So that's going to turn into tetraarsenic. Again, if you want to squeeze those 2 A's into one just to make it tetraarsenic, instead of tetraarsenic, that's fine. And note, this isn't like an "ide." I have to still have the full element name there because it's the beginning one. But my "ide" form, my ending one, is going to be an oxide. And because I have 10 of them, it's going to be, well, decoxide. Tetraarsenic decoxide. And again, the exact way you combine these doesn't matter. If you went tetraarsenic decoxide and you didn't have those double vowels in the middle, I grade it the same way. Your high school sophomores, knowing the nuances of which way vowels get canceled or not doesn't matter to you right now because, let's face it, I understand this is going to be 4 arsenics and 10 oxygens, and that's what I'm after. I'm after being able to communicate. Remember, this is a translation part of the chemistry, not a mastery. So I'm looking for AS4010 when I see tetraarsenic decaoxide. So I've given you 4 more here to do: CO, SF6, N2F4, and GE3N2. I'm going to give you, say, 2 minutes. I'll put a timer on the screen to do these, and then let's throw the answers up on the board really fast. So here we go. So you should have gotten these 4 answers, namely for CO, carbon monoxide, for SF6, sulfur hexafluoride, for N2F4, dinitrogen tetrafluoride, and G3N2, trigermanium dinitride. Okay, let's look at common mistakes for just a second. Some people would still be putting ides at the beginning of this. Remember, the first element never has ide. It's just its name and a prefix if the prefix isn't 1. So down here, these make sense. Trigermanium, dinitrogen, people don't generally miss those. The only mistake that would happen up here normally is people would include a mono, which please again don't when there's a prefix of 1. Ide. Okay, cool, that's all good. Nitride 2, dinitride 4, then tetrafluoride, cool. These top 2, make sure you do include mono when you have an ide. If you have an ide, you must include a prefix all the time. And, maybe some of these are actually pretty familiar to us. Like CO, carbon monoxide. That's the gas that poisons you if you, leave a car running in your garage without the garage being opened or something like that. Sulfur hexafluoride, maybe you know or maybe not. It's kind of popular among YouTubers. It's the opposite of helium. It's a really dense gas. And if you breathe it in, it makes your voice kind of low. It sounds like this.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
My simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that,
and my voice gets really low, although somehow I'm still funny. It's scientific!
Your thought is probably, Mr. Nick, I'd really like you to get some of that, which is great, except it's an awful greenhouse gas. It's really expensive, and it's kind of hard to get out of your lungs in the normal way people say to do it, which is stand on your head, has no bearing whatsoever on how gases would leave your lungs. So we're not going to do that. As cool as it would sound, you can just use an iPad app to change your voice without, having a massive ecological impact or a physical impact. So we got these naming things. And really, honestly, all we have left is to come down here to the second half of the table, down here, and learn how to go backwards, which is actually really easy, unlike it was in ionics, where we had to spend like 2 days learning how to go backwards. Right now, it's going to take us like another 5 minutes. So let's take like another 15, 20-second mental break, and then we'll come in and we'll learn how to work backwards really fast. All right, so that's over. Let's take a look down here at the bottom, the last grid, and we're going to only be on the left side here. We're going to name these 4 chemicals. And of course, those chemicals are over here. In nitrogen monoxide, nitrogen dioxide, tetraboron, trisulfide, and hexasulfur monochloride. Hopefully you can read those, but you have them in front of you. So this is actually super easy. I think it's even easier than going the other way, because all I have to do is look at what's going on. So I've got nitrogen. Okay, that's an N. There's no prefix, so I don't have to put a 1. Monoxide. 1 oxide. The answer is just NO, nitrogen monoxide. It's actually a relatively dangerous gas. It's named well. Whereas nitrogen dioxide, nitrogen, that's still an N, still the same thing as before, but now I've got oxide again. So instead of NO, I have dioxide. So I have NO2. It's really as easy as just kind of reading what's there and working across. So tetraboron trisulfide, boron is B, sulfur is S, so we have, well, BS, snicker, snicker, tetra 4, trisulfide 3, tetraboron trisulfide. Easy. And then finishing off, hexasulfur monochloride, sulfur is S on the periodic table, chlorine becomes chloride, becomes Cl, so I have SCl. And let's see, hexa, I have 6 sulfurs and 1 chlorine. I'm done. And frankly, that's all there is to this. Now, I'm asking you to try these here in the next minute or so. I've got polonium tetrafluoride and others there. Try them. The answers will show up on the board behind me here in 1 minute. Here we go. So I get these answers, namely polonium tetrafluoride, xenon dichloride, dibromine heptoxide, and dibromine heptoxide iodide, like this. And really, honestly, there's nothing too weird here. It's just reading the words as they are. For the most part, my noticing is students get this pretty well. So I'm not going to sit here and belabor the point. A couple of weird things to point out. Polonium is a relatively rare element. You don't find it in a lot of things that aren't radioactive, at least. So this is an extremely rare compound. And xenon dichloride is another one of those weird noble gases bound to a halogen. Turns out chlorine is also quite attractive. And so occasionally you'll see noble gases showing up, although for the most part, you'll just see a couple of those noble or those nonmetals as your starting chemicals. Okay, now at this time your sub is going to pass out a tan sheet. That tan sheet is going to be homework on this, and that homework will be collected on Friday, 2 days to do it. Now, tomorrow you have a full work day. You're going to get the study guide for the test. The test is currently scheduled for next Tuesday, so the day after I get back. And that study guide plus the yellow sheet, you have all 45 minutes in class to do. You'll come in tomorrow and you'll get right to work on it. No big deal. Again, you'll get the study guide tomorrow, if that wasn't clear. And the answers to both should be posted. We'll see how Kairos goes. And then on Friday, you have a quiz. That quiz will be over naming, both ionic as well as covalent, which you just did today. And that quiz you have to pass to take the test. If you don't pass it, you'll retake it on your own time, like after school, until you pass it. Even if you don't have it passed by next Tuesday, you'll keep doing it, and you'll end up taking the test on your own time, which really sucks. So you'd rather pass it before the test, just as a heads up. But that will be about it for it. So hopefully this makes some sense, and if it doesn't, there are a lot of other resources on YouTube that will go through how to do covalency. Or you can shoot me an email, and I will respond, although sometimes a little delayed. Kairos is my first priority over these couple days. And that should be about it. So good luck on this assignment. Good luck on the quiz on Friday. You'll see me on Monday. But this is the last of the videos, the last of the material, actually, for this entire unit. So here we go. Have a good day. Bye.